Welcome everybody. This is our video solution to problem 1 from Quiz 9, Fall 2023, Math 307, Linear Algebra at Cal State Fullerton. And here we are back to finding eigenvalues and eigenvectors. So we're given some operator on R2, and we're told that with respect to some basis, we know what the matrix of that operator is. So it's given here by M of t. And our first job is to find all the eigenvalues. Then we're going to want to find for each eigenvalue all the corresponding eigenvectors. And finally, at least for one of the eigenvalues, we'll show that the corresponding eigenspace is T invariant. All right, so let's handle A and B first, and we're going to actually handle those at the same time. So we're going to use this technique that I showed you in class. So this is a non-determinant way of determining the eigenvalues that is going to give you the eigenvectors simultaneously. So we're going to start by writing down our M of t, right? So I'm just going to copy this again, -5, -3, 6, and 4. And we'll note that if I multiply by the standard basis vector E1, okay, so remember E1 is just going to be 1, 0, then I can just write that down there. If I multiplied this, it'd be the same thing as multiplying t by E1, and that would actually just give me the first column of the matrix. So you could verify if you want, but this is the way it always works. So you multiply this matrix by 1, 0, and you'll get -5, 6. Okay, so at this point, I look at the two vectors I get, 1, 0, and -5, 6, and I quickly establish these are linearly independent. Right? It's just two vectors, and t of E1 is not a multiple of E1. So I'm going to continue on, but I'm going to draw a little line here because I know at this point that if I get a third vector, right, which I'm going to get by looking at t squared E1, a third vector along with the other two has to be linearly dependent because we're working in a two-dimensional vector space. Any three vectors are linearly dependent. All right, so we're going to multiply the matrix, right, because this is the matrix of t, by t of E1 in order to get t squared of E1. So let's see, -5 by 5, -5 is 25, -3 by 6 is -18, 25 minus 18 is 7. And then here, well, it's nice I have the 6 in both, so it's really -5 sixes and 4 sixes, so it's just -1 6. So -6. Okay, so I note now that I have this linearly dependent list, and I'm going to now try then to write t squared E1 as a linear combination of E1 and TE1. So if I want to get one copy of t squared E1, well, let's see, I need to get -6 in the second component. Oh, but that's easy to do. If I just multiply TE1 by -1, -1 by 6 here will give me the -6. All right, and there's no zero, I mean, there's nothing to multiply E1 by because there's a 0 here. Okay, but now, -1 by -5 gives me 5, and I need to get 7. Well, that means I need 2 more, and I can get 2 more by multiplying the E1 by 2. So in total, I get that 0 is equal to what happens if I take t squared, let's see, plus t, right? So we switch the signs on this side, minus 2i applied to E1. So if you expand this out, we would get t squared E1 plus TE1 minus 2E1. And we know that, right, t squared E1 is equal to -TE1 plus 2E1. That's why we get this equality. All right, but now I'm going to factor this, and actually I'm going to factor it in two different ways. They're going to look similar, but they'll be in opposite order. So I can factor this here as t minus I times t plus 2i applied to E1, or also as t plus 2i, t minus I, I'm saying times, of course we really mean composed, also applied to E1, right? It doesn't matter which order we write it down. All right, and I'll keep going one more step here. If I apply t plus 2i to E1, then I'm going to be left with, let's see, well, I can get TE1 and 2E1 by just taking combinations of these columns. So in the first component, I have -5, and then 2E1 would give me 2 more. So -5 plus 2 is -3. second component, the t is 6, and, well, 2 times 0 is 0, so I just get a 6 here. And then down here, I have t plus 2i. Okay, and now I'm going to apply t minus I to e1. So let's see. Here's te1, and then I'll just subtract one copy. So negative 5 minus 1 is negative 6, and 6 minus 0 is 6. Okay, and now we've actually found all the eigenvalues, and we've even found bases for the eigenspaces. Okay, so here we go. It's collected all. So first, we have found two different eigenvalues, right? Namely 1 and negative 2, coming from these right here. Because we know that if I apply t minus I to negative 3, 6, I get 0, which means negative 3, 6, which, by the way, we'll go back to writing it in row form. So negative 3, 6 is in the null space of t minus I. But this is equivalent to saying that 1 is an eigenvalue of t corresponding to the eigenvector negative 3, 6. And down here, we'll have negative 6, 6 is in the null space of t plus 2i. And that's equivalent to saying that negative 2 is an eigenvalue for t corresponding to negative 6, 6. Okay, but I have found two distinct eigenvalues in a two-dimensional space, which means I must have all of the eigenvalues, right? In fact, these two vectors we found, negative 3, 6 and negative 6, 6, actually must form a basis for the space. So we conclude, so this will be now part A, that sigma of t is equal to just 1 and negative 2, so that's the set of all the eigenvalues. And then in B, what are all the eigenvectors? Well, let's write it down here. The eigenspace for t corresponding to 1, right? Well, that would be the span of negative 3, 6. Or if you like things being a little simpler, hey, maybe we'll divide by negative 3, and we'll get the span of 1, negative 2. And how about the eigenspace for negative 2? That will just be the span of, well, in this case, negative 6, 6. And again, if we like, we could divide, say, by negative 6, and we'll get 1, negative 1. All right, and of course, the eigenvectors are the non-zero elements, right, of the eigenspaces. Okay, so finally, we're asked to show for one of the eigenvalues, okay, how about 1, that the corresponding eigenspace, cool, there it is, E of t1, is t invariant. All right, well, t invariant, what did that mean? All right, so U, a subspace of V, is t invariant if the image of U is contained in U. All right, easy enough. So we want to look at, in this case, the image of the eigenspace of t for the eigenvalue 1. So this is the same thing as applying t to the span of 1, negative 2. Oh, but that's actually equal to the span of t of 1, negative 2. Why? Because what does the span do? It finds linear combinations. In this case, it's just multiples of 1, negative 2. And then t is a linear operator, so you can pull multiples out. So you're really just getting the span of this one element. And, well, what is t of 1, negative 2? Well, remember, 1, negative 2 is an eigenvector for the eigenvalue 1. So t of 1, negative 2 is just equal to 1, negative 2. Ah, well, there we go. This is equal to E of t1. And we've shown that t of the image, or t of the eigenspace, is equal to the eigenspace. Okay, that's enough, right? It's t invariant. If it just had to be contained in there, but we know it's actually even equal. So this implies E of t1 is t invariant. Okay? And if we had used negative 2 instead, the only difference would have been when we got span of t of, well, in that case it would have been 1 -1, the image would have been, well, -2 times that, right? We would have had the span of -2, 2. Okay, which actually still would have been the same as the span of 1, -1. So it actually, in that case, T exactly maps the eigenspace to itself again. So there we go. All right, everybody. That was part C. That means we finished the problem. We will see you next time.